Okay, so we're going to talk about the ideal gas law. This is similar to the combined gas law. We're just kind of incorporating one other factor into it, but it's not difficult. So when we say ideal gas law, we're really just talking about gases. We're not really talking about anything special. The main thing is that when we have a real gas, we know that there technically are some attractive forces. They're just very weak, okay, but they are there. When we say ideal gas, we're kind of assuming that there's no attractive forces. So what we're doing, we kind of can apply these equations to real gases because we kind of change the rules just a little bit, and we kind of say, well, we know that in reality there's some forces that can sometimes attract the molecules for very short periods of time, but for our purposes and for the general purposes of gases, we're going to pretend like there's actually no forces or anything that could attract those molecules. So that's basically all we're saying when we say ideal gas. We're just talking about regular gases. There's nothing really fancy. Like the real gas, basically anytime there's it's very hot, high temperatures and low pressure, that's where we get those virtually no kind of forces. We're kind of making it like those particles super fast moving, so those forces can't interact. So that's how we can get to the no forces rule. We kind of ignore those forces. So the ideal gas law is basically how we can just figure out how much gas is actually there. So we're just looking at the number of moles. Okay, so before with our combined law, we were just talking about how the pressure and the volume and the temperature can change. With the ideal gas, it actually lets us calculate how much is there. Okay, so like the amount. So our all of our variables stay the same. We have pressure and volume. We have temperature, and the two new ones are this N and R. N is our number of moles, and then our R is it's a gas constant. So basically what they've done is they've kind of plugged in some standard values, and they've given us this constant that never changes. So what it is it's equal to 0.0821, and this is on your reference sheet in the back of your lab manual. It kind of, as are all of these equations, if you need to look at those, but it's under there. It's the gas constant R. Okay, so anytime we see R, we're going to just plug in this number right here. We've already talked about standard temperature and pressure. It's just 1 atm, 273 Kelvin. It's just kind of a standard value. It's like a shortcut for chemistry. It's easier to write STP than to write out all these other words. So let's do a practice. This is on your notes sheet. Okay, so a restaurant has a neon sign. It tells us our number of moles, our volume, the temperature, and we want to know the pressure of the gas. So we have our formula. And this is kind of funny, but a lot of people call this equation Pvnert. Just to kind of remember the order of the letters. So if you want to say that, that's fine. That's what they call it in college chemistry. So let's just plug in some values here. So I'm looking for pressure, so I'm going to leave that as a P. I have a volume, right? It's 1.52. I have an N, which is my number of moles, 0.431. Remember, my R is always 0.0821. And then my temperature is right here. But remember, I have to add 273.15. Okay, that rule did not go away. I still have to add to get into Kelvin, convert to Kelvin. So 295.35 is my temperature. Okay, so when I multiply all those together, I get 10.45, okay, and then I can divide by this 1.52, Okay, so those cancel out. So my pressure is just the 10.45 divided by 1.52 is actually we'll just go with 6.9. And then our units are always going to be ATM for ideal gas law. Okay. All right, if you want to pause this one by yourself and try one, you can. I'll work it out also, but if you want to try it yourself, go ahead and just pause. Okay, so a sample of gas, I have a temperature here, I have a volume, and then I have a pressure, and I'm looking for moles. Okay, so my pressure is 0.88, my volume is 11. Okay, I'm looking for moles, so I'm going to leave that as N. Remember my R is 0.0821. And then my temperature, I again have to add that 273.15. Okay, so here, if I multiply out, I get 9.68 equals N times 24.5. Okay, and then I can divide by 24.5 to get N by itself. So my number of moles ends up being pretty small, 0.395 moles, okay, of the sample. It has oxygen, right? Moles oxygen. That's a 0, not a Q. An O, not a Q. And then we can actually take it one step further if we wanted to. We could find out how many grams are present. Remember, if we know our number of moles, we can find our grams. So if we start with 0.395 moles of oxygen, remember oxygen's diatomic, there's always 2. I can go from moles to grams by using my molar mass. So 1 oxygen is 16, so 2 oxygens are 32. Remember, that's just like if I was using my mole map. Moles to grams. I'm not looking for molecules, so I'm not worried about Avogadro's number. But in order to go from moles to grams, I'm just looking at my molar mass, and I get that from the periodic table. Okay, that's where that 32 came from. Okay, as long as you can just plug in the values into this formula here, then you're in good shape. And again, just like with combined gas law, if you need any extra help or want any other problems, just send me an email. I don't mind sending you some more practice problems. I just don't want to overwhelm you, when you have a lot of other classes to do as well. If you need to do Google Meet or something also for extra help, just let me know.